For many centuries, scholars studying the natural world shared a very simple, unquestioned method. They simply looked at things. Early alchemists categorized physical matter by its surface appearance. If two materials shared the same color or texture, they were recorded as the same substance. This reliance on sight created a chaotic system. A scholar might grind up two different white powders, expect the same result, and instead trigger a dangerous, unpredictable reaction. Organizing the complex building blocks of nature is impossible if the system relies on optical illusions. Science required a way to uncover the truth hidden beneath the surface. In the 8th century, an Islamic scholar named Jabir ibn Hayyan began encountering physical materials in his Baghdad laboratory that broke the accepted rules of his era. He observed certain solids that remained fixed and stable when heated, even as the common vapors around them vanished into the air. Even in his hottest furnaces, these specific materials stayed solid, refusing to liquefy or flow like molten iron. These outliers forced Jabir to look past superficial assumptions. He needed an entirely new way to define the nature of matter. Jabir pivoted his methodology. He stopped merely looking at his specimens and began applying active, destructive physical stress to them. His first test involved placing pale yellow minerals into a clay crucible and subjecting them to extreme sustained heat inside a furnace. Unlike a metal, these minerals did not melt. Under intense heat, they remained solid until they began breaking apart into a dry, fine dust. Next, Jabir tested their mechanical strength by applying blunt force, comparing the reaction of a copper sheet against a sulfur-based mineral block. While the copper simply folded under the strike, the mineral was obliterated. It lacked all flexibility. It was brittle. By forcing materials to their breaking point, Jabir exposed their true physical properties, providing data that passive observation missed entirely. The ultimate proof of this method came through chemical reactivity. Jabir took two white powders that looked identical to the naked eye and applied a single drop of acid to each. One powder sat undisturbed. The other erupted into a violent, fizzing reaction. This reaction allowed Jabir to isolate a distinct third category of matter, defined by its experimental behavior, which he called stones. Within this category, a material's identity was strictly dictated by measurable properties, such as its brittleness, its heat resistance, and its chemical reactivity. Defining materials by these active reactions created a predictable methodology, changing how scholars interacted with the natural world. Jabir translated the results of these laboratory stress tests into meticulous, organized data tables. He recorded these behavioral properties permanently, noting how different minerals reacted alongside basic illustrations of their shapes. This documentation brought order to ancient chemistry, creating a systematic framework that future scholars could use to identify substances accurately. This shift toward evidence-based categorization replaced intuitive guesswork with a system built on physical, verifiable results. Modern chemistry still groups these exact same materials into categories like salts and chemical compounds. Contemporary science uses atomic structures to explain the very behaviors Jabir first observed in his lab. Today's scientific workforce relies on this same foundation of active experimentation and behavioral classification. While our tools have advanced, the core method of observing and comparing how materials react remains the standard for chemical research. That predictability is what enables the massive scale of modern chemical refining and industrial infrastructure. By proving that every substance must be judged by its actions under pressure, Geber established the logical framework we use to organize and manipulate the material world.